Okay, hi there everybody. So this is part 3 of the homework, and it's a screencast, and it's a short one. This is a screencast that's going to talk about an application, right, of finding max and min, or finding absolute extrema, okay? And this is just the first question from the handout I gave you in class. You can go ahead and take it out. But when you are finding an optimal, okay, when you are trying to find the max or min of something, and here it's the volume, questions that ask you to find the max or min of something are called optimization questions, okay? So an optimization problem is a question that is a type of math problem that asks you to determine an optimal scenario. So for example, if I was looking at a profit equation for a company, and the question said, find the day or the time when profit was optimal. Well, if you're on an optimized profit, do you want to find the absolute max profit or the absolute min profit? Well, in this case, to optimize profit, you want to find the day or the time or the year, whatever the unit is, when the profit was at an absolute maximum. So at the very top of this problem, you'll see it says applied optimization problems. Optimization just means finding the absolute maximum or minimum of something, okay? So what I want to look at here and work through with you is a question, an optimization question. It says an open-topped box is to be constructed from an 8 by 11 inch piece of cardboard by cutting squares of length x from the corners. Find the value of x that maximizes the volume of the box. When you are doing optimization questions, the very first thing you want to determine and answer to yourself is, what is being optimized? Okay, and often the question will give it away. In this case, volume of a box is being optimized. What is being optimized means, what is it that you're trying to find the max or min of? Volume of the box, okay? If you are trying to maximize the volume in this case, you know from our work yesterday, when you want to optimize f, you at the very least have to work with f prime. Okay, if you want to optimize f prime, you at the very least have to work with f double prime. So if we are here finding the value of x that maximizes the volume of the box, right, we need to generate, once we know what we're optimizing, we have to generate an equation that describes the thing to be optimized, to be, in this case, maximized, okay? Optimized means maximized or minimized, okay? So we know if we have to find the absolute max volume, what we have to generate here is a volume function. And when we want to find the absolute max volume function, you know we're going to have to work with the volume prime function. Do you understand? Okay, all of these ideas are from the past week. If we want to find the extrema of f, we have to work with at least f prime. Okay, if you want to find the extrema of v, we have to at least work with v prime. So here, I'm going to make a note to myself that I know the volume of a box, volume equals length times width times height. That is the general equation of a volume. The general equation of the volume of a box. This is called the general. It's a general, or I even call it generic. It's a generic equation for the volume of a box. This is the volume of any box. Any box. Nothing special, just any box. Length times width times height. But what you have to do is we have to contextualize the equation. We need to contextualize the equation from part 2. Contextualize means narrow down every possible box to the box being described here. Contextualize means to incorporate those specific details in this problem that distinguish all the rectangular boxes in the universe from this particular box. And here I'm going to sketch a picture. Well, the context for this problem is we have an 8 by 11 piece of cardboard, and what's happening is we're cutting squares of length x out of the corners. Do you see what's happening here, everyone? We're cutting squares of length x out of the corners. And what happens? What do you think? Well, what happens when you cut squares of length x, what you do is you create these fold lines, I guess, because you can fold the flaps up. And what ends up happening is when we fold the flaps up, you get an open-topped box, right? Hence the emphasis on the open top part of it. We get this box here, okay? And maybe I'll ask you, we're folding, right? We fold up this little flap, fold up this flap, fold up this flap, fold up the flap, tape the corners maybe. And you'll see that the height of the box is x. What's this length of the box and what's this length of the box, or the length and width, if you will? Well, if we know that it started out as 11 inches and this dimension started out as 8 inches, when I fold the flaps up, this length becomes 8 minus 2x, right? Because this length is 8 minus x, fold up this little flap. Similarly, this length becomes 11 minus 2x. Everyone okay? And then what happens here is, look at this beautiful thing. I can now go back to my equation, which was volume equals length times width times height, and I'm going to contextualize. I'm going to contextualize this equation of volume and make note of the fact that the particular length here is 11 minus 2x, and the width is 8 minus 2x times the height, which is x. And now what I have gotten to is the particular equation that needs to be optimized. Here is the volume of the box, and the volume here, which is the dependent variable, depends on the independent variable x. But what does x stand for? X stands for this cut length, right? Now I'm going to ask you here, we're gonna find the value of x that will, what does the question say? Find the value of x that maximizes the volume of the box. We need to find x such that v is absolutely maximized. The volume is as large as possible. Okay? I'm going to ask you this question before I dive in. Whenever we have context involved, I ask myself, are there any kind of commonsensical domain restrictions on x, seeing as how x stands for or represents the length of this cut? Well, hopefully you're all screaming out saying, well, you can't have a cut length of 0, because if you cut 0, you can't have any flap to fold, right? And clearly you can't cut a negative distance. So right away, I know that the domain of x is, oh, why did I do an inclusive 0 after I just said that? Okay, I know the domain is not inclusive of 0, okay? But is there an upper limit on how much I can cut? Let's see. I think the upper limit is 4, right? Because if x was 4, do you see how I'd cut this whole side apart and I wouldn't have any flap? And I guess you could look at this side and say, no, Ms. Yam, but the cut length here could be 5.5. But if the cut length is 5.5 for x, 5.5 is way too big for this side of the rectangular cardboard piece, right? So really, the only domain that makes sense in this problem is 0 to 4, and also not inclusive of 4. And so this is what we mean about reaching that point in calculus where you have to take stock of the whole story. Because if I dove into this and forgot about context, maybe I would find something like, oh no, there's an absolute max v when x equals 228. Circle the answer, move on to the next question, and the person next to you would say, what on earth? How could you possibly cut 228 inches out of a piece of cardboard that is 11 by 8, right? So this whole conversation here was taking stock of the fact that, yes, This particular rectangular box started with this piece of paper, thereby then creating these three factors of volume, where the length, width, and height depend on the original dimensions 11 and 8 and the cut length x. Okay, now I'm ready to do the calculus. I have generated the equation that describes V, and to find where V is absolutely maximized, I know I need to at least work with V prime, okay? I need to get an expression for V prime, or I can write this as V prime of x, or I can write it as dV by dx. Okay, and here's what I'm going to ask you to kind of look at this and scan it and say, what do you think is the easiest way to find V prime? Now, I have my own thoughts, but I think what I'm going to do is, oh, this is so simple, pimple. I think what I'm going to do is, I think I'm going to multiply these binomials and then distribute the x, and then just take the derivative term by term. So when I get there, I'm going to get V equals, let's see, 88 minus 22x minus 16x plus 4x squared, all of it times x, and I get 88x minus 22x squared minus 16x squared plus 4x cubed, which equals 88x minus 38x squared plus 4x cubed, right? I mean, that was relatively painless math to do, and I did that because it's just the payoff is pretty grand. That's V. I'm going to take V prime. V prime will equal 88 minus 76x plus 12x squared, okay? Not forgetting that I only care about, this interval here, right? No points, no critical points where V prime does not exist. So then the question is, are there any values of x where V prime equals 0? So 88 minus 76x plus 12x squared. Set equal to 0. Let's see, does 4 go into all of these? I think it does. Yeah, 4 goes into everything. I want to divide everything by 4. 44 minus, is that 19x plus 3x squared equals 0? Is that right, everyone? 4 goes into, Yep. And now here I have got to solve for x. Oh my, not factorable. At least not that it's obvious to me. Is it though? Let me see. Yeah, not that's obvious to me. I'm going to use the quadratic formula because A doesn't equal 1 and B is odd. And if I use the quadratic formula, and maybe you're moaning and groaning and saying, okay, all over. Whoops, look what I just did. Miss Yam, rookie mistake, rookie mistake. I treated this as A, B, and C. I didn't realize I wrote it in reverse order. Okay, 19 plus or minus the square root of B squared. So 19 squared minus 4 times 3. Oh wait, I don't think I made a mistake. That's so embarrassing. All over 6. Okay, and this is going to equal, let's say, 19 squared is going to be some large number. I had to stop because I noticed that when I divided 88 by 4, I didn't do it correctly. So here's my change here, okay? And guess what? I'm going to use my brain. It's a beautiful brain, just like your beautiful brains. And this is a non-calc active question. I do know, though, that 19 minus some number, 19 plus some number, let's think about this. If this was 19 plus or minus the square root of some number, I think 19 squared, is that 361? I think it's 361. Am I right? Let's check that. Hold on. 19 times 19. Is 19 times 19 361? Oh my gosh, that's amazing. Amazing. So 361 minus, let's see, what's 12 times 22? 12 times 22 is, well, 12 times 2 is 224, so 240. So 12 times 22 is going to be, let's see, what's 12 times 22? I just said not calculator, but I'm just being a little bit lazy. I know I could multiply this. 264, okay. So 264 all over 6, yeah? Okay, and this is going to equal 19 plus or minus 361 minus 264. Is that 97? Radical 97 all over 6, correct? Okay. This number here is approximately 10. So 19 plus 10, which is 29 divided by 6, right? 19 minus 10 divided by 6. Now 19 minus 10, 19 plus 10 about divided by 6, 29 divided by 6. Maybe you're saying, well, this number here, using some mental math, this number here is going to be between 9 and 8. It's 9 and 8. Yeah, sometimes I amaze myself with my between 9 and 10. 19 plus 9 is 28. 28 divided by 6 is a number that is bigger than 4, right? 19 plus 10 is 29. That will also be a number bigger than 4 when you divide it by 6. But 19 minus 9 divided by 6 is a number in this interval. So the only critical point is this. V prime equals 0 at x equals 19 minus root 97 over 6, right? Now we can't stop. We have to show that at this one critical point, and look, if we only have one critical point in an interval, only one critical point, right? If there's only one critical point in an interval, boys and girls, does it make sense that that one critical point then would either be a max or a min, or potentially neither, I guess. But I guess what I'm saying is if there is going to be a critical point over some open interval, right, it's going to be either a max or a min or a point of inflection. But the question to you is, do you want to use the first derivative test for extrema or the second derivative test for extrema? Now I'm looking here at V prime. I am not too keen with mental math taking V prime, making a number line, and plugging in numbers to the left and right of this critical point over this very already small interval. I'm looking at V prime and I'm making a note to myself that V double is going to be a piece of cake to find. So V double is going to equal 24x minus 76. Okay? 24x minus 76. 24x minus 76, let's see. If I think about this number here, right? And again, remembering this number is, that radical 97 is between 9 and 10, right? 19 minus 9 over 6, that's going to be 1 and, okay, so x is between, x is between 19 minus 9 over 6, between 10 sixths and 19 minus 10 over 6 is 9 sixths. Okay, so it's between 10 sixths and 9 sixths. And I'm noticing here that V double prime equals 0 at x equals 76 over 24, right? And actually, you didn't even need to know this detail at all. Sorry, you didn't know that. I'm going to look at this here. X is between these two numbers, and the question is, let's see, what is V double going to equal at this point in question? 24 times 19 minus radical 97 all over 6 minus 76. Will this number be a positive or negative value? Well, let's think about it. 24 times 1 and 4 sixths, 24 times 1 and 3 sixths, okay? So 24 times 1 and 2/3, which is right here, or 24 times 1 and 1/3, which is here. Are you safe in concluding that 24 times some number like 1 and 2/3 minus 76, this is going to be a negative number, okay? Now, let's take a look at this. What we've just shown is the following, is that at x equals 19 minus root of 97 all over 6, comma, f prime equals 0, and f double prime is less than 0. So by second deriv, test for extrema, what must occur? Volume is maximized, right? Is maximized at what cut length? At x equals 19 minus radical 97 all over 6 inches, centimeters, what is this? Inches. Inches. Okay? So applied optimization problems just means applied finding absolute maximum or absolute minimum problems. And they are essentially 3 steps. Note to yourself what is being optimized. Generate an equation that describes what is being optimized. Contextualize the equation. And then do the calculus as you know it, being mindful that this is a real life context, so some common sense constraints or intervals or domain restrictions may apply, okay? All right, that is it. We will continue with this optimization adventure when I see you tomorrow. Goodbye.